Hello folks, welcome to CS-412 Software Security. This is the speedrun for OX01 basic principles. Today we're going to talk about just basic security principles that will help you understand some of the concepts that we are learning for software security, and will kind of let you put away certain areas and let you understand some of the high-level concepts. This is not like super in-depth, but gives you some kind of overview of some of the background concepts and the high-level issues that you should learn. Some of the learning goals for today is to understand security goals, know what software security stands for, be aware of the security triad, CIA, confidentiality, integrity, and availability, and its limitations, reason based on different attacker models and threat models, and understand core concepts that we'll be using throughout the course, like isolation, least privileges, fault compartments, and trust that we have in certain components and abstractions. And then also understand how abstractions enable a reduction of complexity so that we can trust a certain abstraction and then reason about the API that the abstraction actually gives us. So let's dive right in and start with the core definition of software security. Software security allows intended use of software and prevents any unintended use that may cause harm. Right? So this is quite a loaded definition. For this to actually work, we need to know what the intended use of software actually is. This means we need some form of specification to understand what is actually intended for the software, what functionality should it provide, and also we need to know what is unintended and what could potentially cause harm, as in what is outside of the specification of the functionality in the software that we are looking at. Software bugs that are exploitable, that become vulnerabilities, are unexpected behavior of a program in response to certain inputs. The exploit then arises when an attacker can provide input that causes behavior that they desire, which is opposite of the behavior that is intended by the developer. As in, the attacker can provide certain input to the program that then causes a bug to trigger that allows the attacker to execute behavior that is not following the intended behavior of the developer, but actually compute something that is desired by the attacker. Now this is very abstract, but it could be, for example, you have a mail program, and instead of sending a mail, the attacker provides certain input that triggers a software bug in the mail program and lets the attacker read arbitrary files, for example, mails of other people that are on the same system, or execute other programs that are not intended as part of the mail program. Right? So for software security, we need to know what is the intended behavior and how do we define the underlying boundaries. Right? What should the program actually do and what should it not do? And how can we detect if it does something that it shouldn't do? A long time ago, in the 70s and 80s, the US government defined the CIA triad. Right? This is the basic triangle that is being used to discuss different kind of issues for security. And if you look at a system, we still try to reason as a baseline. Even though the CIA triad is already a bit dated, we try to reason along the CIA triad. It's a good start, right? It's like an estimate. And for this course, it suffices to follow the CIA triad. The CIA triad focuses on the original CIA triad focuses on 3 dimensions: confidentiality, as in the attacker cannot recover any kind of protected data. On the example of the mail server, it would be the attacker cannot read any mails of other users that the attacker shouldn't be able to read. Integrity, as in the attacker cannot modify protected data. For example, after having sent an email, the attacker cannot modify the email that is now stored on the server. Availability, an attacker cannot stop or hinder computation. And again, with the example of the mail server, this would be the attacker cannot terminate the mail server and prohibit the other user from reading their emails. Recently, what we added to extend the security triad is a fourth fundamental property, and this is called accountability or non-repudiation, as in committed changes cannot be undone. So after having sent an email to the server, the attacker cannot undo sending this email. So the attacker cannot lie about not having sent the email. So as in there's some kind of commit log that tells us, hey, this person has sent an email and this log cannot be undone. A quick note, confidentiality is that the data of someone keeps hidden, right? So the data remains protected and hidden. Privacy would protect the data of a person, right? So if we talk about privacy, then we would say that, hey, this actually involves a person. And anonymity protects the identity of a protocol participant. So these are all slightly different nuances of the same concept. Confidentiality focuses on the data of someone, right? Or some entity of some object, right? So confidentiality protects some data. Privacy protects the data of a person, as in, for example, your username, your password, your social security number or whatnot. And anonymity would protect the identity of somebody who plays like one of the email users, right? In the example that we just looked at. Now, if we analyze the security of a system, how do we decide if a system is secure? Right? This is a very broad and open-faced problem. And it's without any kind of structure or guidance, it's hard to argue if a system is secure or not. We have to reason about the attack surface, first and foremost. What kind of API or interface does the target software expose? So what kind of input can the attacker access? Right? So the attack surface defines what inputs the attacker can access. We also have to reason what the assets are, as in what could the attacker gain? Like how much effort will the attacker put into how much worth does the data have that the attackers could get? And also what are the goals, as in what drives the attacker? And we will formally analyze this as part of a threat model. And the threat model defines the abilities and resources of the attacker. The threat model enables the structured reasoning about the attack surface and allows us to write down what the possible issues are. For this, we need awareness of the entry points, like what are the exposed functionalities and what kind of inputs can the attacker trigger, what are the limitations of those, and possible associated threats of them. We look at the system from an attacker's perspective, right? So we decompose the application, we identify the structure, clearly write down what kind of functionality the attacker can trigger, determine and rank different threats, different issues, and write this all down explicitly. And then, in the last step, we determine countermeasures and possible mitigations, as in how we handle each of the threats. And if the risk is low, we can simply say, oh, we anticipate this through legal concerns or through technical measures or by rewriting the application to protect against a certain angle. If you want to read further on this, I recommend the OWASP article on threat modeling. So let's work through an example. We've got a safe or a lockbox, and we want to protect our valuables by locking them in this safe. What's the attack surface of this safe, right? And if you do have a safe like this, there's possible ways to attack it, right? I'm sure you can come up with a bunch of them. We brainstormed it a little bit and came up with a couple. In a trust land where everything is safe, you don't need to lock your safe, right? You can just leave it open and everything will be fine. So under this threat model, everything is safe and you don't need to protect it. An attacker may pick your lock, right, by attacking the lock of the safe, right? So this is part of the exposed API or the exposed interface that the safe provides. An attacker may be able to attack it. And this would be confidentiality and integrity if they break open the lock. An attacker may use a torch to open your safe, right? And this would destroy the safe in the process, while picking the lock may be stealthy. An attacker may use advanced technology, as an X-ray, to open it and learn what the key combination is, right? So this would use a certain technology to break and leak information about the safe and the inner workings of the safe. An attacker may get access or a copy of your key, right, by for example stealing it or photographing it or learning this information through another way, right? So without actually attacking the safe, the attacker may be able to get information in using a side channel. Then an attacker may steal the whole safe by just grabbing it and running away with it, or an attacker may replace the safe with a copy of it and then open it somewhere out of bounds, right? So as you can see here, depending on the threat model and the resources of the attacker, there's a lot of different scenarios that are possible to open a safe and lockbox. We've argued along the provided interface, right? There's a door, there's a lock, there's potentially a key, and there's the safe itself. And then we can argue about this API and how the attacker can use this API and interface to gain access to it. If we reason about security, there is no free lunch. Any security incurs overhead. So security for software is expensive to develop, right? It costs additional resources, it costs developer cycles, expensive to maintain, because all the added code needs to be continuously maintained as the software is being used and being adjusted. May have performance overhead due to additional impact, due to additional computation, due to additional storage requirements and whatnot, and may also be inconvenient to users, right? So this all comes at an additional cost. And we have to reason if the cost is actually worth it. Now, today is gonna focus on some of the basics, right? And we are focusing on 4 basic security principles that are somewhat intertwined and depend on each other. Isolation, least privilege, fault compartment, and trust and correctness. And I usually visualize this using a ship, a modern-ish ship, as you can see on the right-hand side. Modern ships have compartments, right? These are individual fault compartments that break the hull of the ship, reinforce the hull of the ship, and break the main body of the ship into different compartments. So if there's a hull break, only 1 or 2 compartments will flood, and the remaining compartments will remain closed. There's going to be locks, so the API, the doors between the compartments will be closed, and thereby protecting the ship against sinking, right? So this will ensure the buoyancy of the ship, even if 1 or 2 of the compartments are compromised, right? So this isolates incidents and ensures that individual compartments can fail while still protecting the overarching goal of the ship's design, which is staying afloat, right? So let's go through these principles in a bit more detail. Isolation is the principle of isolating 2 components from each other. So one component cannot access data or code of the other component except through a well-defined API. If you think back to the ship, this would be the 2 compartments next to each other can only access each other through the door that actually opens between them. Another example would be a user space application may only access the disk, the hard drive, through the file system API, which the operating system provides. You don't want the user space application to have raw block access to raw data on the disk, because otherwise an application could read arbitrary data from any arbitrary user. The operating system therefore isolates the user space process from the disk, but still provides access to data on the disk for long-term storage. Note that isolation incurs overhead due to switching costs between, for example, the user space application and the operating system kernel. So this comes at a cost, right? So user space processes are isolated from the hardware, and the operating system orchestrates hardware access and interposes between the user space application and the operating system and the hardware resources, thereby abstracting them and providing only limited access to it with security checks. And the security check obviously comes at an overhead. Similarly, the address space and the process abstraction separates processes from each other. So two processes in user space cannot access the data and code of each other, except through a well-defined API through the operating system kernel, by, for example, sharing part of their address space with each other. The second principle is the principle of least privileges, or POLP. Like, the principle of least privileges ensures that a component has the least amount of privileges it needs to function. So, for example, with a processes are isolated, but they do not necessarily run with least privileges. A process can run any arbitrary system call it wants to that are allowed to a given user. So this is not least privileges, but gives you a convenient way to execute a lot of privileges. So you could install a system call policy that limits each process to only the few system calls they actually need. Right? So this would limit the system calls to a few, this would limit a process to a few system calls that are actually needed with the properties that they actually need. This would then enforce least privilege. For a process running under least privileges, any further removed privilege, so for example, if you would remove an additional system call, would reduce functionality. Any added privilege, on the other hand, will not increase functionality according to the specification. Right? So this property constrains an attacker in the obtainable privileges and requires isolation. For example, the Chromium is broken into many different processes, and rendering in Chromium of the HTML pages executes in an encapsulated sandbox where only a minimal set of system calls are allowed. And these system calls are read, write, close, exit, and sig return. As in, only memory that has already been allocated can be used. Data can be read and written through pipes or through file descriptors, and these file descriptors can be closed. And last but not least, the program can actually terminate if it needs to. Right, so this is an extremely limited sandbox that ensures that bugs in the parsing code for all of these HTML pages and for the rendering can actually be contained and make it as hard as possible for an attacker to escape out of this sandbox. The next principle is fault compartments. Like, fault compartments, as you've seen in the ship, is that a large monolithic component is broken into a set of compartments that are then isolated from each other. So we separate individual components into the smallest functional entity possible. These units contain faults to individual components. So if a component is buggy, then the bug will be restricted to the individual component. And this enables abstraction and permission checks at the boundaries. So instead of having one large monolithic process that runs as a server, we break the server into multiple small processes to communicate with each other. So if there's a bug in one process, this process will crash, and we can then terminate the daemon and the other processes based on some high-level decision. This property builds on least privileges and isolation. Both properties are most effective in combination. Right? We need many small components that are running and interacting with each other with least privileges. But then the more components that we have, the more overhead there is for switching costs between the individual processes and between the individual components. Right? So there's a trade-off between security and performance. And this needs to be carefully designed to hit the sweet spot between not too much overhead and still having reasonable performance. Okay? Now, the last principle is trust and correctness. So specific components are assumed to be trusted or correct according to specification. For example, as a user-space program, we would trust the operating system to be correct. The operating system would trust the hardware to be correct. On the other hand, we could use formal verification to ensure that a component correctly implements a given specification and can therefore be trusted. Right? So for example, we could have a small privileged component, like an operating system, that is formally verified and can then be guaranteed to be free of any kind of bugs, according to the specification, of course. It's generally not computationally possible to formally verify arbitrarily complex software. So for example, verifying an operating system of about 10,000 lines of code took 10 to 20 man-years to person-years to actually verify it and ensure their correctness. So 20 person-years to check and verify one single simple operating system. Also, the specification may be buggy or may be limited, right? So a formal verification can only be as good as the underlying specification. We rely on hardware and software abstractions, as I just mentioned before, that allow us to reason only about a subset of the components, right? Abstraction is the act of representing essential features without including the background details or explanations. Abstractions allow an encapsulation of ideas without having to go into the implementation details. The abstractions require an explicit definition on how to interoperate between layers. So for example, if you look at software, the API abstracts the underlying implementation by defining how a library can be used. And you're likely using the C library, you may be using a threading library, you may be using a database library. There's a lot of libraries. And instead of having to understand all the low-level implementations, you're using the exposed API to access a high-level abstraction, a high-level interface. We do the same in operating system. The operating system provides the system call interface to abstract away the low-level implementations and to make it easier for us to access hardware and to share hardware among many different processes. And on the hardware level, the ISA, the instruction set architecture, abstracts the underlying implementation of instructions into logic and state. So you don't want to reason about individual transistors. You simply want to execute an instruction, right? So this makes this much easier. You can simply encode your program as a set of abstractions instead of having to encode it as a set of logic with the NOR, or whatever other gates you want to look at. So let's talk about some abstractions, and the most important one that we will use is the operating system abstraction, which provides a process abstraction, right? And it gives us a well-defined API to access hardware resources, enforces mutual exclusion to resources. So for example, if you have a printer, the operating system will make sure that only one process is allowed to communicate with the printer at a given time. And this is usually the printer daemon, which then provides a rich API towards other processes that can communicate with the printer daemon to then send individual print jobs that are then being spooled, put into a spool directory into a queue, and then being printed one after the other. The operating system enforces access permissions for resources. For example, not everybody is allowed to access the screen, not every process is allowed to access the screen, not every process is allowed to read the keyboard, and therefore there's individual restrictions there. Restrictions can be enforced based on a user or a group or access control lists. And this restricts the attacker. As in, if there's a bug in a user space program, the attacker cannot immediately take over the complete system, right? If there are some abstractions there, right? This is an additional boundary between a user space program and the overarching system, thereby limiting how fast an attacker can spread, right? So a single bug or a crash in a program is contained to user space, and the attacker would then have to find a second bug in the operating system to escalate their privileges. And this is being enforced by the operating system process isolation, right? So there's processes running next to each other in their individual address spaces, and the memory of each of the processes is actually protected, right? So the memory of each process consists of code and data such as heap stack or globals that are then being placed in a single address space for one process. And between processes, these address spaces are actually protected. So going from one process to another process, we need to communicate through the operating system to either share a part of our address space if we want to do so, or to just communicate through pipes by always going through the operating system to communicate. And the address space is local to each individual process. Today's systems implement the address space through virtual memory, through page tables with the help of a memory management unit. That is a hardware extension that makes this actually fast. Otherwise, the address translation could be implemented in software, but this would be awfully slow. I refer to your operating system course for more details on page table, memory management, and the address spaces. But for this course, we just need to be aware that the operating system provides a process abstraction that gives each process an address space, and the address space is unique to this process. To communicate between two processes, we can use different kinds of inter-process communication, or we can share a part of the address space. Now, there's different kinds of operating systems and operating system implementations. And we'll just quickly go through the 4 kinds of operating systems that we are currently using. There's a single domain operating system, which is a single layer that's the simplest form, a single layer. There's no isolation or compartmentalization between things. All code runs in the same domain, and the application can directly call into drivers. So for example, there's the application code that directly interfaces with the scheduling code, the file system, memory management, network driver, disk driver, USB driver. And these drivers then interface with the hardware. But there's nothing that would prohibit the application from accessing the hardware directly. So this is often used on very limited devices. Think embedded systems or industrial control systems or IoT devices, right? These are very resource constrained devices and usually geared towards a single task, right? So if they only need to control your fridge, they don't necessarily need a full-blown operating system with app support and internet connectivity. So it suffices for these devices to run the simple core application, and it's only the one application that they are interested in. A monolithic operating system consists of 2 layers, right? The operating system and the application. And here we see there's multiple applications interfacing with the operating system, and the applications no longer have direct access to the underlying hardware. They have to go through the operating system for all hardware access. So the operating system separates the applications from the hardware. The applications are unprivileged and must request access from the operating system. And this Linux and Windows are examples of such an approach of monolithic operating systems. And this is predominantly done for performance, because isolating individual components in the operating system itself is fairly expensive. There are some pushes towards making Linux and Windows somewhat compartmentalized, but they are a bit slow in coming. Micro-kernels further break systems and kernels into small individual components. Here there's a lot of different layers, right? Each component is a separate process. There's a somewhat of a core operating system that implements scheduling, virtual memory, and IPC. These are the core features that are implemented, and only these core features have direct access to the hardware. On top of these systems, there's a set of user space processes and daemons that implement the disk driver, the network driver, the USB driver, file systems, and whatnot that communicate with each other. And the applications then communicate with these other processes, right? So in a microkernel, only the essential parts are privileged. The process abstraction, which provides address spaces, the process management, which provides scheduling, and inter-process communication to provide communication between the individual processes. Right, so this abstracts this further. This is the most secure implementation that gives us a way to break complex operating systems into smaller components and ensuring that if, for example, the disk driver crashes, the file system can happily continue and is not compromised. But this comes at the cost of inter-process communication, as in if the disk driver communicates with the file system, data has to be copied between address spaces, which comes at a certain overhead and a certain cost. The last abstraction for operating system is a library OS. And here the assumption was that we follow a microkernel design where a very thin operating system exposes bare operating system services and only does scheduling, virtual memory, and IPC. And the applications then leverage a library OS to interface with these components. They get somewhat segmented hardware access as given by the scheduling, virtual memory, and IPC components by the microkernel, and therefore much higher performance, right? Bundling a large chunk of the operating system with an application allows us to improve some performance. And this is a trend in virtualized servers to reduce the cost of virtualization and to speed up these operating systems that are used there, especially for single-use virtual machines. They don't necessarily need a large and complex operating system for that, right? So this is part of a system optimization for that. So the hardware there's a set of hardware abstractions that we are using for this. We implement virtual memory through a combination of the memory management unit and the operating system, and only the operating system has access to raw physical memory. We use DMA for trusted devices to allow them to communicate and write directly to different memory areas. We use the instruction set architecture to enforce privilege abstraction, right? So the different privilege levels that allow us to distinguish between the operating system and user space application, and to switch between user space and operating system are special instructions on top of the hardware. So the underlying hardware, the ISA, provides these abstractions to implement privileges. Without hardware support, it would not be possible to efficiently implement such an operating system. So we rely on this for speed and performance. So these hardware abstractions are actually fundamental for performance, and we require those to implement all of these abstractions. Now they give us, like these are abstractions that allow us to efficiently implement security primitives on top of it and to separate these components efficiently. Now let's walk through an example after all this theory and the set of the different privileges, so that we can talk a bit about how we can efficiently use these abstractions and principles to make sure that we can protect servers or software. And we'll talk about a mail transfer agent, a mail server, and an MTA needs to do a plethora of tasks, right? So this service needs to send and receive data from the network, as in there's new emails coming in that can be sent from other servers that we're receiving from somewhere outside, and we want to send emails that are being queued from our local users, right? So a mail transfer agent runs locally. It receives new emails from the network and it sends emails to the network from our local servers. We need to manage a pool of currently received and unsent messages, and we need to provide access to the stored messages for each user. As in, like there's going to be hundreds, thousands, tens of thousands of users on a single system, and we need to provide access to each user's mailbox, and each user should only be able to access their mailbox and not the mailbox of somebody else. Originally, SendMail was the first mail server that was used on all these systems, and it follows a typical Unix approach where it provides a large and monolithic server, and it's also known for its very high complexity and a large set of security vulnerabilities. This SendMail has been around for 40 plus years, and it can still be used today, but today better alternatives actually exist. Now, if you think about this, like there's a lot of different functionalities, a lot of different tasks that a mail server needs to do. And I'm sure they can be compartmentalized. Now, how would you compartmentalize such a mail server? You may want to pause this and think for a second. And a good way to compartmentalize a mail server is as follows, right? We've got the network side and we've got the local side. On the network side, there's one process that's listening on the network port, that is qmail SMTPD, which listens for outside connections to receive any new emails. This runs as a specific user, qmailD, and it receives the emails, buffers them, and then passes these emails as a file to qmailQ and pipes the emails to qmailQ. qmailQ is a SUID program, so it has special permissions to run and store emails as qmailQ, allowing it to change the permission of the file of the data it receives. It then passes the email to qmailSend, which then decides if the email needs to be sent or stored locally into a given user directory, or it needs to be sent remotely. If it needs to be sent remotely, it spawns a new process that then sends the email as qmail remote, which sends the email, which receives the email and sends it to the network. rspawn only receives the email through the pipe and then spawns the actual remote program that is only handling the network connection. That way, the storage, reading, and sending can be separated. On the local end, there's qmail-inject, which runs as the local user, that then calls qmailQ to store the email. Now, the interesting aspect here is that qmail-inject does all the parsing, same as qmail SMTP. So they parse the headers, figure out if everything is correct, and only then pass it to qmailQ. So if there's a bug in qmail-inject, which is more complicated, then an attacker wouldn't gain anything because they are only running as the local user. So they don't get more privileges than what they already have. qmailQ then is a very simple program that simply stores the email in the queue and then passes it to qmailSend to read emails in the queue and then spawn it. If it's being delivered locally, qmailSend will invoke qmail-lspawn, which runs as root, which simply stores the email in a local user directory. lspawn figures out which user it needs to send it to and then sets the user account of the given user. Right? So there's a very limited set of permissions here. And you see this is a somewhat complicated or large set of different processes that all have individual tasks. And all of these are individual processes or daemons or tasks that run in isolation. So all of these processes are isolated from each other. So qmail SMTPD is isolated from qmailQ and can only communicate with each other using a clearly exposed API. There's least amount of privileges for a given process, right? So it runs as an isolated user and is restricted in what it can actually access. Here it can only access, QMLD can only access the network and is only allowed to call QMLQ with a pipe, but is not allowed to access the local file system. And the process runs in a actual fault compartments. If there's a bug in QML SMTPD, it will fault and the attacker will only have access to the network but not to the local file system. Right? So there's a limited set of privileges an attacker can gain. Overall, this example here trusts the operating system and the OS process abstraction, leverages the process abstraction to break a large, complex, monolithic component into a set of individual tasks that are isolated from each other, that are running with least privileges, and that provide fault compartments if a bug should happen, that an attacker cannot escalate and directly access the other components. So all of these separate components run under separate user IDs and are isolated from each other, right? So these are this is a way how you can split a large and complex system into a set of smaller tasks that are limited to their individual functionality. This just summarizes some of the aspects that I just talked about and gives you a bit more detail. Now that we have talked about how to apply compartmentalization, isolation, and least privileges to a mail server, let's talk a bit more about access control. Right? We've already hinted a bit at this with the different users and whatnot that the processes run under, and we'll make this a bit more explicit here. Right? Access control consists of 3 steps: authentication, as in who are you; authorization, who has access to an object; and audit provenance, I'll check what you did. So access control consists of these 3 steps. First, we need to authenticate somebody to this to figure out who that person or who that entity is. Then we need to authorize. Only a subset of entities will have access to a given object. And then we can check and audit, as in after you have accessed, I can actually check that you had access to it and everything is okay. So let's talk about these 3 components step by step. And we'll start with authentication. There are 3 fundamental types of identification. One of it, what you know, what you are, and what you have. And what you know is something that you remember, right? A token that I can give you, a secret that we share, right? And this can be a username or a password, right? This is a secret that we share between the 2 parties, and the secret is then being used to authenticate. We can use something that you are, for example, biometrics, your iris, your fingerprint, your whatnot, or we can use something that you have, for example, a smart card, a phone, access to a phone number that receives text messages or whatnot. And authentication is stronger in combination. Using 2 factors, for example, username and password, and some SMS, a text message to authenticate the presence is better than 1. 3 factors may be better than 2 factors, but then there's additional cost of the actual security to check all of that. So a good way is 2-factor authentication, checking for username and password, and the presence of a security token. And this can be either a smart card that you have, a YubiKey, or a second factor through a text message or a one-time password that you may be using. Some of the pitfalls that we have to look into is that not every secret is a good secret. So for example, a social security number, your retirement number is a unique global unchangeable identifier. In most countries, this is somewhat of a secret, but if it leaks, it's very, very hard or next to impossible to change. Same for biometrics. Biometrics are unique and unchangeable identifiers. So if they are leaked to somewhere else, there's no way for you to recover this information and to retain the information against an attacker. As soon as the biometric information is leaked, an attacker can simply recover it and then use it for identification on their end. Loss of social security number of this information or biometric data allows replay attacks. As soon as an attacker has it, it is no longer secure. Right? So, for example, knowledge of a social security number in the US allows an attacker to open credit cards and lines of credit in the name of the victim, which is something you don't necessarily want. So a key lesson that we have here is that authentication must be mutable, as in we need to be able to change it if it is lost. It needs to be updated and adjusted. After authentication, we also need authorization. And authorization centers around information flow control, as in who can access what information. And access policies are called access control models by defining how and which entities are allowed to access a given object. These access control models were originally developed by the US military in the 70s and 80s. It supports multiple users with different clearance levels on a shared system. Data is shared across different users and levels of clearance. And this keyed the name multi-level security, or MLS. This was a big thing in the 80s, and most of the research in security in the 80s actually centered around multi-level security, which given the limited systems of the time was somewhat crude, but fairly essential for them to actually enforce separation of multiple users. As in, if you had trusted and untrusted users on the same system, you needed to make sure that they can actually access their individual objects without interfering with each other. There's different kind of policies for authorization, and we'll discuss two fundamental types of access control: mandatory access control, MAC, and discretionary access control, DAC. These access control models can be hierarchical and form role-based access control models, as in RBAC that we'll look at. Let's start with mandatory access control. And here the idea is that they are pretty much centrally controlled. They are rule and lattice-based policies controlled by a central administrator, and only this administrator controls the permissions that are given. Users cannot change the policy themselves, right? They're only allowed to access the system. The administrator may set permissions for each file, as for example, a hospital owns patient files and specifies who can access these individual files, right? Only doctors are allowed to access the full file. Nurses are allowed to access medication information. The patient is allowed to access only a subset of it, right? So there's going to be different kind of restrictions. There's two specific examples that were discussed that have a slightly different implementation. There's Bell, LaPadula, and the BIBA access model. Let's talk about those in a bit more detail. Right? Bell and LaPadula is a multi-level security model that enforces information flow control. How information can flow between individual entities of different security levels. This requires that all security levels are monotonically ordered, and each object or each file has a clearance level. A given clearance allows you to read objects of lower or equal clearance and write files of equal or higher clearance, right? So for example, if you have secret clearance, you're allowed to read secret files, sensitive files, and public files, and you're allowed to write secret and top secret files. And this, if you think back of the CIA triad, enforces confidentiality. Now you have to obviously be a bit careful that an attacker cannot override confidential files, right? But this gives you confidentiality of this information. So an attacker, if they had access, cannot leak information, right? They can read all of the public, sensitive, and secret information, but they can only write secret and top secret information. Now, on the other hand, BIPA is a multi-level security model that enforces information flow control, but it enforces integrity. A given clearance allows reading files of higher or equal clearance and writing files of lower or equal clearance. If you have secret clearance, you're allowed to read secret and top secret, but only allowed to write secret, sensitive, and public information. So compared to Bell and LaPadula, BIPA enforces integrity. So files are protected, right? If you have a given clearance, you're not allowed to modify files of higher clearance, right? But here the issue is the attacker may leak privileged information. So you have integrity but not confidentiality. With Bell and LaPadula, you have confidentiality but not integrity. And this is one of the interesting issues that people discovered in the 80s and were wondering about. Now, so much about mandatory access control. So the key lesson for mandatory access control is that there's a central entity that assigns the policy. For discretionary access control, or DAC, the roles are a bit flipped. The object owner specifies the policy. While MAC requires a central control, DAC empowers the actual user. The user has authority over their resources. So we introduce ownership. The user owns the given data and can set permissions of the data if other users want access. This can become quite complex and require per file special casing. One good example of discretionary access control are Unix file permissions with user, group, and everybody else, right? So this is a simple example of discretionary access control. As a specialized example, role-based access control allows the definition of roles, right? So this means a DAC or a MAC policy defined in terms of roles. So instead of having to define the permissions for each object across all the different users in a humongously big matrix, as in which user has access to which files and what kind of access they have, we define roles. And a role gets a given access, and then a user gets access to one or multiple roles, right? So the roles are authorized for given tasks. And this allows us a simplification. We only need to define the different roles and then what roles a given user has. Access permissions are broken into sets of roles. Users get assigned the specific roles that they have, and the administration privileges may be a role that allows them to modify the roles. This massively simplifies special cases, but roles can still become overly complex. For both role-based access control and classic models, a matrix can be used to specify and map access rights for users to objects, or users to objects to roles, and users to roles, right? For example, in a Unix or Linux file system for Android, iOS, Java security, or Android, Java, iOS security model for privileged APIs, they use different kind of access control matrices. This has been introduced by Butler Lamson in 1971, and I actually highly recommend the paper to read. Let's summarize of what we discussed today, right? The software security goal is allowed intended use of software and to prevent unintended use that may cause harm. Again, we need the definition of what is intended and what is unintended as part of a specification. We talked about the security triad along confidentiality, integrity, and availability. We looked at the security of a system dependent on its threat model. and talked about core concepts such as isolation, least privileges, fault compartments, and trust. Security relies on abstractions to reduce complexity, and for the different kind of access control, we learned about discretionary access control and mandatory access control with a refinement for role-based access control. And as a reading assignment, I would recommend you to look through Butler-Lampson's file paper on protection, which is a great read and stood up over time. Thank you very much, and see you soon for the next iteration of software security.